I want to continue with the Game Boy assembler that I started, and the last time, where did we leave off? Well, we kind of needed a hash table um, to recognize assembly operations in our assembly file, and we found this Pearson hashing hash table that I tried to implement, which had like this permutation lookup table, and it was just an 8-bit hash table because I thought, okay, let's use that because we don't have that many commands anyways. But when running it, realized that there were a few collisions, so I wanted to play around with the permutations and see if we can reduce the collisions and actually get rid of them. But in the meantime, yesterday I was looking up a few other hash functions, and I actually found a better one that I think we will be using because it is much simpler. It allows for 32-bit hashes, which is excellent, and so we can just focus on implementing the table itself. And the cool thing is, I could then mix symbol names with actual command names. I don't have to maintain two separate tables later on because we would have needed a proper hash table anyways for all the symbol names that we can specify. So symbol names, just to uh, explain like real quick, is just if you want to define specific regions in your assembly code to jump into, you can give it a specific name. Let's say, for example, main loop, right? You specify a region that's called main loop, and then somewhere you have a jump instruction where you then say, okay, jump to main loop. So then the code can kind of resolve that jump based on the name. So that's what I call symbol names. Essentially just a location in memory. Later on, could extend these symbol names to be variables or things like that, or like little defines. Whatever I choose to implement, basically, whatever I feel I need for my assembler. Um, yeah, I mean, why talk about it too much if we can just jump in, right? So let's go here. Whoops, what did I do there? Okay, so I found this little website here which lists a few simple to use hash functions, more or less. It's on cse.yorku.ca. I know, very easy to remember the name, right? um, but essentially, what we'll be using is DJB2. This is all that is to it. So basically, it starts out with a fixed number in the beginning for the hash, and then it iterates over the string character by character. And essentially what it is doing is, I'm not sure if that's even visible. Let me zoom in. uh, what it is essentially doing is it multiplies the hash by this magic number 33 and adds the byte of that character into it. Um, Now it says here multiply by 33, but as you can see, what it's doing here is like a shift left by 5 and then add the hash to it and then see. This is basically another way of writing hash multiplied by 33, because a shift over by 5 is essentially the same as saying multiply this by 32, right? Because we're shifting all the bits, so you essentially just multiply it by 32. And because we want to multiply by 33, we can just add hash once more. And then we have effectively done a multiply by 33 with just a shift instruction and a plus. Apparently this runs a bit faster on some hardware. I have not verified this. I have not looked at the, how many cycles each of these instructions take and whether this is actually faster. But Since this has been long time in use, let's just assume it is, right? I assume all these people in com.lang.c, Dan Bernstein here, knows what the fuck he's doing, right? So we're just gonna copy that. Yes, okay, so I think we can just start with the table. I've not even opened the project yet, apologies. Oh, and Sublime Text is updating, but I don't want to do that now. Okay, so let's remove what we did last time. So this hash table here, I kind of have a better way of doing this later on anyways. And we also no longer need the permutation table. Nope. What we'll be using is DJB2. Actually, let's add the URL to this. So I know how I can make attributions later. It's DBJ2, right? No, DJB2, sorry, by Dan Bernstein. I guess that's just his name. D for Dan, B for Bernstein, and then J, probably his middle name. Who knows, right? And then we can just use the hash. So what we need is an unsigned long, so that would be U32 in my world, right? Because if you look at the type defs, I have a U32, which is just unsigned int. Int, again, is just basically a long. It's kind of interchangeable here, but okay. We still take a U8 value, yes. And count. Yes, I want to do that because I don't necessarily... So I want to be able to calculate the hash even on null terminated things, right? So then, actually, let's kind of... Whoops. Sorry about that. Let's open this like this. Okay. So we need a U32, which will be our hash, and we initialize it with this magic value right here. And then what we'll be doing is a for loop where we go from size ti equals 0, and we go to count, and we will increment this as such. And then we just have hash and shift it over by 5, which is multiplying it by 32. Add the hash to it, that will be multiplied by 33, and then we add our value I to it. Cool. So let's also comment out this for now, because I kind of want to change the struct that we're using a little bit. Let's just see if the hash is doing what we think it's doing. Over to the main. Right, we had all this test code written, which is fine, I suppose. Let's see, what are we doing here? Oh, we're creating entries. Right, let's remove that. Let's remove this. Test is still a good thing to have. Iterate over all these names. The hash is now a U32 instead. And Right, we need to pretend that we have a hash table. So let's do, I mean, let's just do that. Let's just call it table. And table has a fixed size for now on, let's say, but let's keep it small and see what happens, right? I mean, there will be collisions, no doubt, if I do this. But I kind of want to approach and see if I can increase the table and see when I start to not have collisions. So table hash. Actually, it is this, right? Right, okay, it's just a char, fine. Why complaining here? Oh, because I still have value in here, right? You don't have that. But it is essentially a two-dimensional array, right? Because it is an array of char pointers, and a char pointer itself can be accessed similar to an array because there could be multiple characters. So we can just do that. If this is not 0, there will be a collision. How can we make it 0? Well, no, actually. Let's do that. And we don't do this. Okay. And then table hash, but we need to wrap around because now it's, since it is 32 bits, it can be quite a large value. And obviously our initial table will be smaller than that. So we kind of need to wrap around. And you can do that with the modulo and then the size of the table. And actually what we should probably do is have it defined here. Hash table size, right? And then we can use it like so. And the hash value will be, we don't need to do the string copies because we can just point to values.i instead. Whatever. Okay. I'm not sure if I need to do this to zero everything out. And let's remove the printing for now. Okay, so test. Can make a breakpoint here. Oh, right, I wrote example code last time of how we would use the hash table and actually look for operations and stuff, but that's not needed right now. So let's just do this, and we get an access violation. Why are we getting an access violation? Because I'm a genius and did not do the wraparound over here. Fantastic. Okay. All right. Yeah, there is a bunch of collisions. Actually, it would be interesting to see how many collisions. So let's count that. I like to use size t for any counter things, but any integer is fine, right? Collisions. Start up with null, and then every time we have a collision, let's just increment. how to misspell collisions. That's something else. It appears I need more coffee. I'm a bit tired today again. I was out and about all day yesterday, so I'm a bit exhausted, but all good. We're getting through this. Okay, we have all this, so we can just say printf. There are %lu collisions and collisions. Cool. So that, whoa. Hang on, I forgot to turn off all my alarms. Fantastic. Be quiet. I do want my coffee alarm still. Let's keep that one on. Okay, so there's 31 collisions. All right. So what if we do table size 256? Right. 14 collisions. Okay. How about this? Still 6 collisions. Okay. Does that in any way decrease if I do this, for example? 0 collisions. Okay, cool. Collisions in itself are not unexpected, and they're fine to have. Hash table size this big. I don't know if the initial hash table size should be that big, but anyways. Our hash function is working. That is good. I would be surprised if it didn't work because this is used apparently in a lot of places where we just need a simple hash. Okay, so now I can think about what do I want to populate the hash table with, right? And what will be my resolution for collisions? Let's probably start with that. So collisions. A collision essentially just means we have the same hash for 2 different keys that could possibly have different values. For example, we could have key foo and key bar, and they could end up with the same hash code, right? Well, why did the collisions actually get reduced when I increased the table size? Well, that is simple, because we are wrapping around on the table size, so eventually, you know, if the table size is too small, there's a higher chance for the keys to end up in the same slot, essentially. So one way to resolve collisions would be have the entries have a linked list and still store them in the same index, right? But I'm not sure I like that very much. Because that would mean I have to, for every entry, for every hash table entry, I would have to allocate it on the heap and then have a pointer to it. At least I imagine I would have to allocate it on the heap. I'm not quite sure on that one. Depends what I'm doing with the stack variable, I suppose. Yeah, anyways, I don't want to think too much about it. Another way would be, even though it could result in slightly worse performance, I do not care right now, would be to just increment the hash by 1 and occupy the next slot if it is free. And if it isn't, just go through until you find the next slot um, that's unoccupied. So basically, a linear search. Uh, if the table is completely full and there's no more space to be had, uh, we'd have to increase the hash table. So by reallocating it, let's say double the size, for example, would be one strategy that I usually used with my dynamic arrays, for example, when I needed a list or anything like that. And then just go through all the elements of the old table and insert it again into the new table. So probably realloc wouldn't be a good thing to use, to be honest. But yeah, since this is just from compiling and it's not something that needs to run in a super tight loop, right? So it's not like we're doing this every single frame within a video game or anything like that. I think this should be fine. Famous last words, right? Well, so here's the thing. If it turns out to not be fine and this turns out to be a bottleneck for some reason, and assembly of my Game Boy games or whatever takes like incredibly long time, we can just go ahead and like implement a better hash table, right? Then we can go into the table stuff and resolve collisions in a different way. So I'm not too worried about all this stuff. YOLO, as the kids say. Good God. I'm dating myself. I don't think anyone uses YOLO anymore. I hope not, at least. Okay. So, type div struct. Actually, let's just rewrite this one, right? I mean, we already had it specified, so why not? So this is a table entry. And what do we want in that table entry? Well, for one, we want a symbol name, right? And let's say it's 256 characters at max for now. A hash. Yes, we need to store the hash as well, because if I use linear searching, excuse me. Oh, and because the table in itself is smaller than the hash, we kind of need to store that information in case, like, if we do the linear search and stuff. So yeah, we definitely need to have the hash in there as well. Okay, here I already had the pointer to like handle collisions, but let's not do that anymore. And how do we find out whether it's occupied or not? Because if we just allocate a table with all these entries, we need to figure out a way to say, okay, this is occupied or it is not occupied. And I guess I could just go as I did before with the other one, is just check the first character, and if that is a null character, then this thing is unoccupied. I think that should be okay. It just means that we're not allowed to add null strings essentially as a key name, which, why would you want that anyways, right? It doesn't really make sense. So and then later on, we kind of need to, you know what, let's not name this name. It's a key, right? It's a key, it's a hash. Okay, and then we need additional information at some point to, you know, add the items that we're actually storing in there. In our case, it is symbol names. So I mean, the key is technically also the symbol name. But then we kind of maybe want to know, okay, what kind of symbol is it? Is it an operation? Is it a register? Is it a user-defined symbol? Anything like that, right? But we're not gonna worry about this for now, or do we? Okay, let's do. And instead of hash, let's give this a better name. It is symbols, right? This will be our symbols table. So compute hash name size t is in the CRT stdlib.h is the name. I mean, yeah, let's leave it the name, whatever. So we have the compute hash function, and this is actually a symbol. Yeah. Okay, let's do the enum as well now. So GBA symbol type enum. And we have GBA symbol type operation. User, symbol type name, symbol type user, as in user defined, symbol type label, okay, we named the word, so let's do that, temporary name, right? In the tokens, we have this word token, which is just temporary. So let's just do the corresponding symbol word. This might be different symbols. So there might be like labels. There might be, I don't know, aliases, for example, variables, this kind of stuff. So we'll probably fill this up with a few more types than just this. But, and then we have the GBA symbol type. Just type. Okay. The table itself. I'm wondering if I should put that in the header as like a global to access from everywhere. I mean, not really anything wrong with it, but I'm not sure if I like it, but actually, GBA symbol table struct. I realized also, because I need to dynamically resize it, I need to keep track of the size so to see whether it's full or not. And the capacity, I suppose. Yeah, okay. Symbol table, let's call it entries. And then we have size t capacity and size t count for the amount of entries that are in there, I suppose. Yeah, that's fine. Okay, then we have bool. Include std bool.h. In its symbol table. Okay, and this will be similar to the buffer that I wrote. As you can see, the structures are quite similar, right? We have something that is our pointer that we allocate on the heap. We have the capacity, and the other thing we have here is the size. And we can use the same process heap and heap alloc functions that we called in here. So in a sense, we can just copy this actually and rename it. Okay, we probably want to use size t here. I mean, it's the same type, so it doesn't really matter that much, but we want std window, right? So we can use size t here as well for this and this. Okay. Don't like compute hash being all the way up there. Okay, so in it, symbol table, I suppose. We have the capacity. Do we have alignment size? Do I want to care about this? Sure. I mean, it's already in there. Might as well keep it, whatever. Doesn't make... I'm wondering if this alignment size was actually useful or not. Whatever, let's keep it in there. Get process heap, yeah, we do that. So, heap alloc. So what is capacity? In before we just, I was just allocating bytes. So the capacity was just a one-to-one mapping to the bytes. But now we actually have structs, right? So the real capacity is, well, we have to times this by size of the size of the struct we actually want to allocate. So that will be the capacity in bytes. Do I want to store the real capacity in bytes in here, or just say, no, there is like this many elements there? I think I just leave it with this many elements. Okay, so, and then what we're getting back will be a GBA symbol T pointer. And this is not the buffer, this is the table. So we have table capacity and table entries. Table capacity. If table entries is null, something went horribly wrong. And then we have table count of 0 because we have no elements in there. This won't be the case. What I want to do is add operations to the table, because those will always be the same, right? And we have GBA free symbol table. I should have kind of switched these names around. GBA buffer init, buffer free. But it is what it is right now. Let's not get too hung up on this. We learn for next time. Okay, so here we have the table. This code is actually quite simple because all we have to free is sorry, no, not the symbol, we want the table. All we have to free are the entries. Okay. Cool, so we got this. We can now initialize a table on the heap and we can free it from the heap. So now we want to be able to insert items into this, right? So GBI insert symbol. So I'm thinking, when I'm paused like this on a function definition, I usually try to think about all the failure modes first. Like, how can this go wrong, right? Oh, okay, we have this, and we probably want to add a symbol. The question is, do I just pass in the name as a pointer? And should this just be pointers? Yeah, I want to copy the whole thing. But we can probably say name like this and size t name size name count. Name length, jeez. Okay. So we probably need to do a little string copy right here, where we take the name and copy it into the symbols table, into this thing right here, which is not too bad. So strncpi. So we probably should still include CRT. String, what am I doing? String.h. Right. Destination will be, well, first we need the hash, right? So we want to add a name to the table, so u32 hash, and then we have GBA compute hash, and the hash is of this name right here with name length. Actually, naming this length is way nicer. Okay. Let's just name it length. Symbol length, whatever. Simple name, symbol length. Okay, cool. So now we got the hash. Now we can figure out the index into our array of entries. So that would be this, and it would be hash modulo of entries, nope, of table capacity. Okay. So the naive way of, let's not, worry about collision right now. Let's just get this without collisions done. So that would be table entries, and it would be on this index. And all we do is hash equals hash. Actually, we can make this a bit nicer if we say this is a GBA symbol T entry, right? Like so, but we want the address of this one. And then it would be entry hash equals hash. So now we're just basically filling out the information. We want to know the type. Well, see, okay, we need to give the type in here as well. So let's do that. That would be the symbol type, right? And then we have oh, key. I named it key. It's a name, for crying out loud. Naming is hard. Okay, but for name we need to use string copy. So what we want is probably strncpi. The destination will be, well, the entry name. We can also use the safe one so the compiler doesn't complain, because I'm pretty sure it would if I wouldn't put this in here. Size in bytes we specified as 256, right? This is probably a good usage for define, where we can say max symbol name length 256. Let's just say max symbol name. So max symbol name. The source will be the name that we just passed in, and the max count we want to copy is length. This, however, can fail, right? So if this is not null, something went wrong. Let's just make like a quick thingy like this. Actually puts. All right, make a breakpoint in here, and let's see how we can make this fail. So okay, I no longer need this file open here, but you know what? Let's make a few tests. I think I did those last time, but I completely forgot. So let's just test 2. Right. Let's just do a few of these. Ernity arrow 1. Cool. So 2, 3, 4, 5, 6, 7. However many I need. We have a buffer. Let's say child name, and it's 256, right? Cool. Actually, let's make this something more manageable for the test right now. So let's just do 4. This would just be name. And then we have, let's say, we have nothing in here. We have 1 character in here, right? We have 1, 2, 3 characters. We have 1, 2, 3, 4. We have 5 characters. And then we have 3 characters, but we only copy 1. And then we have 1 character, but we want to copy 5,000. And that's it, I suppose. Okay. Cool. All right, GBA hash is now called symbols. Yeah, that should be it. Okay, cool. See, and we want to avoid situations like this. All right. So this would return an error of 0, right? Because it just works, whatever. Name would just be null. Okay. 1 character copy works just fine. Actually, let's put name down here. Does it though? What? Oh, because I made this pointers. Jeez. Sorry. Okay, that was dumb. Yeah, so this would be 0. This would be A0. Cool. ABC 0. Fantastic. Now we are ABCD, and this is where it fails. Okay. So we kind of need to shorten the symbol name, so we're truncating it. But rather I should represent to the user, okay, no, your symbol name is way too long, this is not allowed. So probably something in the lines of if length is bigger or equal to max symbol name, because we need to account for the null character. Or do we? Yes, we do. So this needs to be 3, right? In order to work. Of course, I didn't finish the code. Jeez. Yeah. And then it will be truncated, but we don't want that. Okay, so yeah. So if it is bigger or equal than max symbol name minus 1, then this is a no-no. Return false. And this is where it gets a bit more complicated, because we want different error return types. Because, so it could fail the symbol name is too long. Or this string copy somehow failed. Sorry, what are the failure reasons? Actually, I should have just looked that up. How about that? Source destination would be null. I mean, if that happens, we have far bigger problems on our hand. Or if source is null, again, far bigger problems on our hand. Mm. I mean, okay, let's realistically think about this. This is not just characters, right? It is actually unsigned 8, right? U8, because I want to allow UTF-8 encoded names here. So using string copy is not really what I want anyways. But this is still correct. And what I want is basically memcopy. Because we do not care for the null character whatsoever. Okay, so memcopy probably has similar behaviors than the string one. So if any and count is 0, return is 0. Okay. If null or any, yep. If any or null, okay. So this could potentially go wrong. Probably only if name is null. But it will already blow up anyways if we compute the hash. So any is smaller than count, then this will fail as well. Okay, hang on. So with memcopy then, the thing that failed before should work, right? So let's make this U8. This is already complaining because of the size. Fine. There you go. Okay, let's do that. So this would return 0, right? Okay, this just works. ABC just works. Shoot. I want to make this 4. Okay, this now should just work. And indeed it does. This should fail. Right. Okay. What if I do this in release mode, by the way? Still. I'm surprised it blows up so hard. Ah, right, sorry, debug. I thought it was maybe just because of the debug mode, but nope. Yeah, it literally just terminates the process. Okay. Okay. I mean, it kind of makes sense, but okay, let's keep this in then, and I can say max symbol name because we no longer need to account for the 0 character because we treat this as UTF-8 formatted string, and we do not give a crap about the 0 character, as I just said. So instead of const char pointer, this will be a const u8 name. And yep, and we use memcopy right here. Okay. Otherwise, everything worked fine. Okay, so this is how we add symbols into the table without collisions, right? So we do not check for collisions just yet. And we can test this code right here. So instead of doing the compute hash and shit like that, what we do is we have GBA symbol table T, table, and we call GBA in its symbol table with a capacity of so this avoids collisions, right? This size, alignment size. Sure, let's do the same one. The table is the address of the table. Fantastic. And then we can call GBA insert symbol into our table. The name is values I, and the length is strlen of values I. Okay, and if this fails, then we increase the collisions for now. And then in the end, because we're nice, free symbol table. Okay. Nope. Too few arguments in this. Oh, because we need to specify the symbol type. Correct. My bad. It is symbol type operation. Okay. And now if we look at the table, we have entries. Well, that will be quite hard to find all the entries right now. Okay. Can you do that? No. Can't display it as an array. Well, that's okay. But now I need to also, crap here, because this is a UTF-8 name. I also need to keep track of what the actual size of that name is. So what we want is a size t of name length. Yeah. CP and length is 2, and the rest is just garbage data. So another way to do this, instead of an array of like, max symbol name, I could just put every single name on the heap. But I don't want to do that. I think this is all right. Okay, so we can insert symbols into our table, but we do not account for collisions. So how do we check collisions, right? What's the way to do that? Well, one thing to do would be, so we're computing the hash. We're finding the index. We're getting the current entry. And now if entry name, the name length is not 0, then collision. So what we possibly want to do is have a for loop that is the index. Well, our index will be that thing. So then we have, if index is smaller than table capacity, we go through. So this will be search the bottom half of the table for an unoccupied slot. Sorry, this is index plus plus. Then we're fetching the entry of that current slot, and we check so this will be a collision. So let's say if this is the case, we don't have a collision. So we go through until we find an empty slot. table. And we will churn out of this loop. So if we ever reach the end of the for loop right here, we have exhausted all the bottom options, but there might still be space in the top, right? So let's do it this way. Now this is fine. Okay. Search top half of the table for an unoccupied slot. So then we do this from the bottom, which will be index equals 0. And then if index is smaller than hash percentage table capacity index plus plus. Right? Because this is the original index and we want to search everything from 0 up to the original index. So, and there we do the same thing. We're getting the current entries, we're checking if the name length is 0, and if it is, we just add the symbol name to the table. So what happens here? Can that ever happen? Well, in theory now this means our table is full. So increase it. And this is where the fun begins. To do increase hash table, and then what we want to do is probably call GBA insert symbol again with the current table, with the name, with the length, and with the type. Because increasing the table will mean we shuffle all the elements around, which means we should probably do this computation again. Now, this means in the worst case now we compute the hash twice. But I mean, it kind of is a serious case anyways, because we're increasing the hash table, we have to like do a bunch of memory copies and things like that. So calculating the hash twice there is the least of our worries. Okay. So, I mean, here we can just copy the code, whatever, it doesn't matter if we have duplicate code like this. It's fairly simple code anyways, right? So we're doing a mem copy. If this mem copy fails for some reason, then we give up as well. So ideally this, so if this mem copy fails, there is something wrong with the symbol size name anyways, but this should already be covered by this case, so I don't think we will ever be able to reach this one. So this might be just a bit too defensive, but whatever, let's just leave it at what it is. Okay, and then we need the same code down here. Okay. But in order for this insert symbol to work, we need to have a way of increasing the hash table. So let's write that next. So GBI, let's say grow symbol table, right? Because we reached our max capacity and we want to increase it. So So I'm just thinking, if we have all those elements in here, I only have GBA insert symbol where we need to calculate the hash of the name. But I might need a function which accepts already an entry, so it can just be copied. So something in the lines of GBA reinsert symbol. And that what we have here is a GBA symbol T that we want to insert somewhere. How about GPA insert symbol instance? So for that, we just need the index and the symbol hash. And then we have the searches going on. I don't like this. I might just rewrite the insert in this grow symbols table. I think that's the best thing to do, honestly. Otherwise, it kind of mashing up two different concepts here. Okay. So, grow symbol table. What do? We have a table and we have a capacity, and what we want is a size t of new capacity, right? Because we want to increase it, and at the moment our growth strategy is just double the amount of space that we actually have. So now what we can do is we can allocate a whole new table. So we would call GBA init init symbol table, and yeah, we have new capacity. The alignment size, well, yeah, let's just leave alignment size out, whatever. table capacity is capacity. Done. Let's not worry about the alignment size. That was kind of a weird thing to do anyways, so let's not worry about that. And here what I forgot to do is for table, I need to increase the count because we now added new items to the list. Okay, and here is room for some optimization with a short circuit, right? Where we can simply say if table count equals table capacity, oh boy, we should be doing something. Table is full, so increase it. But hang on, then this can never happen. Okay. Yeah, there's no way this can happen. Okay, that's one to watch out for, I suppose. Okay, so we have a new table with a new capacity right here. I do not need to initialize a whole new table though. Yeah, I can't call this. I need to call get process heap, correct. What we're having is a temporary entries. Call this new entries. We allocate this with the new capacity. And then if new entries is null, then something happened, but we do not touch this one, right? So now our steps will be copy elements over and free the old entries and done. Okay, so let's copy elements over. Let's hold on to the old entries. Right. Then we have the new entries. Okay, if this succeeds, then table entries become new entries, which just switching out the pointers. Table capacity becomes the new capacity, and size t old count is table count. Table count is now 0. Okay. Let's group them a bit better. Okay, so we're holding on to the old entries. We're holding on to the old count. We get the process heap. We define a new capacity that we want, which is just double the old capacity, right? And then we get the new entries table. And if that succeeds, then we switch out the old entries table for the new entries table and the old capacity for the new capacity. And we also reset the count to 0. And now what we need to do is for I equals 0, I equals is smaller than old count. So we're basically going through all the table entries, the old entries, and try to insert them into the new hash table, right? And for that we call GBA insert symbol. And what we need is the table, which has now the new size and everything. Ah, right. This is where I wanted to copy the code. Okay, never mind. Okay, so to do insert all elements. And then, once we inserted the old elements, we need to free our little table right here, which will be the old entries. Process heap, yep, and old entries. Cool. So how do we insert the old entries into the new table? Well, we just copy these two for loops right here. First, we search the bottom half of the table for an unoccupied slot, and we can do this because, well, we have an index. Yeah, let's do it this way. So index is old entries number I dot hash modulo. Before it was the table capacity. We can still do that because table capacity is now the new capacity. So this will be the new index. We get the symbol pointer right here. And if entry name length is 0, we need to make sure that it actually initializes as 0, because at the moment it does not. Huh. What does no serialize do? Ah, heap 0 memory. Okay, that will be a bit more costly. No, we don't need to do this here, sorry. We need to do this allocation. Does this work in C? It should, right? That just means copy whatever is here over to here, since it's just a struct. Okay. And if that is the case, we do table count plus plus. And then we say continue with the loop. Well, we'll continue this loop, right? Ah, shit. um, I think this is time for a helper. Yeah. GBA symbol T. Find unoccupied slots in this table from start. Okay, find empty slot in symbols in entries. Find empty slot in entries. We have the starting index. Let's call it offset. No, let's call it, yeah, let's just call it index, whatever. And then we have size t, which is the maximum. The limit. So now we can put these for loops that we have right here in here. And then we have whatever index is pointing to limit, and whatever index is pointing to will be increased by 1. Okay. Then we have entries and whatever index is pointing to. And then we just return. So probably we need a bool here. Okay, so return true, we found an index. Otherwise, return false, we didn't find an index. Cool. So let's use that in the GBA insert symbol. Right, we have table entries. Our index will be the address of index right here. And our limit is table capacity. Okay, and if we found something, well, if we didn't find anything, and we didn't find anything again, we have an error. To do this can never happen, right? But the second one is shoot. Yeah, no, we can do it like this. And then we can say index equals hash table capacity again, because we have to reset the index. And only then it is a failure. Otherwise we fall through. And what we're falling through to, well, this little thing right here, where we can say the entry we found is the index that we got back by this function right here, by these two searches. So where we search the bottom half, and then we're searching the top half. And then we do the same thing as before and increase the table count. Okay, cool. looks a little bit nicer now. Okay, and we just copy all of this for up here. So we go through all of our old entries and then we search the bottom half for table entries, the index, and table capacity, correct. And then we reset the index again. And then we search the top half. And if this fails, okay. This would cause a memory leak now. So probably what we want to do, if for some reason this goes wrong again, I probably want table entries to be old entries, table capacity to be well, table capacity divided by 2, and table count equals old count. And then we should whatever happens here doesn't matter, right? But we should free new entries. Okay, anyways, at some point we have an entry, and then hopefully we can just do this. Old entries I. So table count plus plus. Okay, so we're going through all the old entries. Once we're done with the old entries and everything went all right, we can return false. What we can do is we can have an. Do I want to add an assert? Nah, let's not bother. I mean, you could add an assert to see if the new count is actually the same as the old count, but I think this is fine because, like, if this fails, we just bail out completely anyways. Okay. So here, grow table, we can say GBA grow symbol table, and we can pass in just the table. If this fails, we cannot insert. So once we grew the table, we can just try and insert the new thing right here. Cool. I just realized I should probably have compute hash up here. Anyways. There we go. Okay. Now, to make this hash function or the symbol hash table actually more complete, what we would need here is like remove entries from the hash table, right? And the other thing we would need is look up entries. I do not think that I need to remove entries ever. Because let's think about it. This is an assembler. We're just opening one text file where we go through everything, and we're adding symbols as they are defined in our source code, right? So we're just adding. We might do like lookups. Oh, does this name already exist? If it does, then do not add it again, whatever. We just add. And like, I don't see a reason why we would ever need to remove symbols. Because the symbol needs to be known the entire time we parse the file, up to the very end. And once the file has been parsed and our ROM has been assembled, the program ends anyway, right? So there's no reason for us to hold on there's no reason for us to ever delete anything out of that table. Okay, so let's make a lookup. GBA find symbol, and we pass in the symbols table. And to know what we look for, we need the name. And definitely the name length. This is just one of the things we fucked up. Because we're using UTF-8 encoded strings. Ideally, we would like wrap that in a string type somehow, but let's not bother with this right now. Find symbol. And then what we can do is just have GBA symbol T and return it, right? And if this returns null, the symbol was not in there. So how would we look up symbols? Well, we start by computing the hash, same as with inserting. Get the index. And once we have the index, we now need to perform searches similar to here, right? So let's just copy this for a second. Search the bottom part of the table. So we have the index. The index is smaller than table capacity. And we just increment the index. Okay, cool. So this is how we search for the bottom part. Now, we receive table entries from that. We receive the entry from that particular index. And the first thing we check is if entry hash. No, we already know it's the same hash, right? So what we will need to do now is compare the bytes. We can do some other things. So right. So if in that slot, so how do I explain this? We computed the hash of a value. We found the index in the table of where this value is supposed to be, but it could be a collision, right? So the value is not exactly the same. So what we need to do now, we know we have the same hash, but now we need to compare the name to see if it is actually the same value. To do that, we have a few shortcuts. For example, name length we can look up. If the lengths are the same, then the value is probably the same. So what we now can do is memory compare, right? And we're comparing buffer1, which is entry name, with the name we have right here. Is it mem_i copy? Compare, sorry. Let's look at the documentation. I've never used memory compare before, so let's. Okay. I mean, we already know the name and length are equal, right? So we can just say length, whatever. We already know that is the case. So, and if the name is equal length and the contents are indeed the same, then we found the index of the symbol we're looking for, right? So what do we return here? We want to return the symbol. Exactly. So that will be just entry. So return entry. Now, if this is not the case, then because our insert strategy is if there's a collision, just use the next slot, but then we need to find the next unoccupied slot, right? We have to do the same thing. So it could just be a collision, so it might just be some slots further down. Now there is a case of like, uh, in the worst case, right now, it would just go to the very end of the table. Even though maybe it doesn't need to, because there might be some unoccupied slots there in between. So one thing we need to look out for is unoccupied slots. So if entry name length is 0, then this slot is unoccupied. And since we do not have any deletes or anything like that, we don't need to worry that, this might be like some weird state or anything. The name length is 0, which means we do not need to look any further. So we just return null because the key we're looking for is not in there. Unless everything is full and we go through the same thing, then suddenly we are in a situation where we need to check the top part of the table. And what we're doing here is we're basically saying index is 0. And actually, I just realized this was complete bollocks what I was doing here. Because what I want is this and set index to 0. Right. So I need to change that up here as well. This is this. No, sorry. It is this. And index is 0. Whew! Well, that would have been a nasty bug. Okay. Right. So index is 0, and we need to go to this. We find the entry, and we basically do the same thing. So if we find an unoccupied slot, then this is like no, 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 no. And otherwise, only if the lengths are the same, then we do that. And if we do not find it, we return null. There we go. This is our lookup. I think this is all of it. Oh, and this, yeah, that was dumb. It returns 0, doesn't it? Yeah, but 0 is false, so what I was doing here was not great. We need to do this. Also up here. Right, and I don't have that anywhere else. Okay. I just realized that the insert was also a bit rubbish that I did here. Because I do not just want to find empty slots, right? Because what if the key is already in there? And it is actually the exact same thing that I'm trying to insert. Right, so I kind of want this whole thing as well. So if oh dear. We also want to compare the hash, to be honest. So if name length is okay, look up. Let's start again. Um, if the name length is 0, it is an unoccupied slot, so we can determine that this symbol is not in here. Otherwise, if entry hash is the same as hash, and entry name length is the same as name length, and yeah, then this entry exists. Okay. Whew. So as an explanation, because hash could be something different, because it could be occupied by a previous thing that we shifted down, right? Right. Oh my lord, this is getting quite complex. Okay. Find next slot in entries, entries, index, limit, name, name length. Okay, so we're going through all of this, we're getting the entry. If name length is 0, this is an empty slot, so we can actually use this. However, if entries hash is the same as I don't like this function. Hmm. There's a way to make this a tiny bit nicer. GBA find slot for symbol. Where did I do? Where did I use it as well? I used it in grow table, correct? Yeah. Okay. GBI insert symbol top. And GBA symbol. What we do have is size t index equals symbol hash modulo table capacity, and then index smaller than table capacity, index plus plus. Table entries index, we fetch the current entry. If name length is 0, we just add it. So in this case, we just say this equals symbol. Check if slot is empty, or check if slot is the same. Okay, let's do that. Why not? So entry hash is the same as symbol hash, and entry name length is the same as symbol name length, and mem compare entry name and symbol name is the same as symbol name length. Okay, and if it is, this is entirely the same thing. Well, he says. really what we want is an equals method, right? So let's have an equals method. And then we can just say, well, just this right here. If a hash equals b hash, if a type equals b type, if a name length equals b name length, and a name equals b name with b name length, then those things are truly equal. Yeah. Otherwise, return false. Okay. So then here in find symbol, we can say if GBA symbols equals, what do we have? We have entry, and we have well, no, here we can't do that because we do not, right, here we just literally check for the name and nothing else because we're just looking up a key. Find symbol by key. By name. And that is my coffee timer. So I'm gonna go for a coffee break real soon. But let's just get this done. Okay, we have find symbol by name. That seems to be correct to me, right? So if the thing is empty, we just return null because we haven't found it. Otherwise, we compare the hash, we compare the name length, and then the name itself. And if that is correct, then we just return the symbol that we just found. Otherwise, we return null. And we search the bottom part of the table and the top part of the table. Seems to be nothing wrong with that. Famous last words, probably plenty wrong with it, but in the confines of this project, nothing wrong with it. So insert symbol, let's ignore the grow table. What are we actually trying to do? Well, we're computing a hash, and then we're trying to right. Here we actually do want to use equality of everything, so type as well. Because we want to make sure we're not adding the same thing. Does that matter? Hang on, it might be a different symbol, but same name, but it might be a different symbol, right? It might be a user-defined symbol. So that makes no sense that I'm checking for the type as well. Oh man, this is super annoying. Okay, let's make this symbol name equals. Because the hash is also just the name. So, and then we can use this down here. And let's mark this as inline. Okay. So if entry, but then I need to initialize a whole new struct for this thing. So, no, that doesn't make any sense either. I feel like I'm now overcomplicating things. Let's see here. So, check if the symbol is empty. I mean, if I actually want to insert it, it would make sense to make a new symbol. Let's call it insert. And we have insert type is type, insert name length is length. We have insert hash is hash, and we have a mem copy of the name. Which is insert name and name and the length. Right? Okay. So insert symbol top. We do exactly that. If we find an empty slot, we just assign it. Otherwise, we just want to use symbol name equals. Entry and symbol. we're going to the bottom of the table. So if the name is equal, like truly equal, so the hash is equal and the name is exactly one-to-one the same, then this thing already exists, right? So we should probably say false. And if it's no, but then we would start searching at the, oh man, I guess I just say true because it's already in there, but that's kind of misleading. Do I just overwrite it? I feel like that's what most of the hash tables are doing now. You can just say, fine, whatever we have in there, overwrite it. Yeah, because we might want to change the type or whatever. But then, ugh, this is disgusting. So I'm looking for situations like this, right? We have a command that's JDA. Now, let's say someone creates a variable that's called JDA. This would be type operation. This would be type user. So then suddenly the user variable would override the operation, and suddenly that operation is no longer valid for like the entirety of the assembly process, which would be nuts. I. Okay. GBA insert symbol. Let's just not worry about all this growth stuff or how we compute the hash or anything like that. We have a symbol, it has a hash attached, we're trying to put it into the table, right? First thing, search for space at the bottom part of the table. Search for space at the top part of the table. Right? Just copy this. index is 0, and we are going to this is our okay, symbol is empty. Let's just plug it in, return true. If it is the same name, return false. We couldn't insert anything because it already exists, so you shouldn't be using it. It's a redefinition or whatever. So true, false, true, false. And now we exhausted all the possibilities, so there is no way we can insert it for whatever reason. Just false, although I'm pretty sure it might not be possible. Okay, this is our insert symbol. And now we can make a convenience thing. Actually, no. This is how we insert symbols. Let's look at the growth one first. So growth table, GBA insert top, we do not need. Okay. Right. GBA growth symbol table. We have old entries and an old count. Actually, it would be easier instead of doing it this way around. Okay, we get the process heap, and then we start doing this. And what we might do is this actually already initializes everything for us. Let's not worry about this. Okay. Let's create entirely a new table. So a symbols table, which would be nope, not a pointer, it's a new table, whatever, right? We initialize it with a capacity of table capacity times 2. And if this fails, this should be an address, then we would just return false as well. Okay, we have our new table. I can get rid of the heap alloc right here. Let's just make this all a bit simpler. This was nonsense as well. So now need to iterate through all the symbols in the old table and plug it into the new table, right? So for size ti equals 0 equals capital T. That would be table no. Table capacity, I suppose. Yeah, because we want to copy all the entries, no matter what. Grow symbol table, maybe no, because if we allow to specify capacity, we could pass in something that's smaller than the last table, and then we would actually shrink the table, which is not what we want to do. Right, table capacity, plus. Okay. Then table entries I, and we plug that into the new table, so we can say GBA insert symbol, and we plug this into the new table and pass in this symbol right here. And if this fails, well, then we can say GBA free symbol table and free the new table and return false. Right? So now we copied the symbols around. Then what's left to do? Well, what's left to do now is go to shoot. You know what? Instead of bool, let's return a new symbol table. We're taking a table in and we're returning a table. And that is my doorbell, so I'll be right back. Okay, I'm back. It's always annoying when you get ripped out of in the middle of coding, because then my mind needs to realign. Oh dear. I don't know. No, I probably don't want to do that. Let me think. How do I do this? So GBA table free. Where is it? Free symbol table. It only really frees the entries, right? No, I can do it. I can do it this way. Cool. Right, so we copy all the elements over to the new table. Okay, now we have the new table, but the old table is, well, it's invalid, right? So what we do is GBA freeze symbol table and say, well, free me the old table, because we no longer need those entries. And then we can go ahead and be a little sneaky and say, well, the old table entries are now the new table entries. And then table capacity equals new table capacity, and then table table count equals new table count. Although count is probably still the same. Yeah, count will be absolutely the same, so just need to do this. Cool. And then we say return trip. So this looks a bit nicer, doesn't it? At least in my mind it does. Okay. So we have grow symbol table, we have insert symbol, and then we have find symbol by name. Well, we have a table, we pass in a name and the length of the name, and this is where we do like, right. We have a name equals. Okay, but we can't use that here because otherwise we would have to construct a whole new symbol type. And we do not care about the type because we're just trying to find an element in this moment. Okay, this is cool, but now I still want to be able to, I mean, does it matter if I have to construct the symbol beforehand? And presumably table growing I can just check as well. Well, it would be nice to have a convenience method, right? Insert symbol. What to name this? Insert symbol by name? No. Well, I can think about the name later. Essentially what I would like to do is combine insert symbol and grow symbol table, right? So I put in the name. First I check that the symbol name is actually the actual length, otherwise we fail. If table count equals table capacity, then the table is full and we need to increase it. which is where we call GBA grow symbol table. If this fails, all hope is lost and we could not insert this item. Then we create the symbol type right here. Copy over the name. And then we can just say return GBA insert symbol into this table. And the symbol we want to insert is inserted. On GBA table insert, did I do the... Of course I did not. Table count needs to be incremented right here and right here. So this down here now is like a convenience where we do the growing of the table if it is full at the same time as inserting it. Which is nice to have. Init symbol table free symbol, okay. Grow symbol table. Then we have GBA insert symbol. Find symbol by name and insert symbol by name. I mean, yeah, I think this works. Okay. Let's test it. Yay. Okay, main. How do we start? So we have a symbol table. Let's set the size to 2 elements. Right, that will be interesting to see what happens. And then we can sort of step through this. So we have init symbol table, then insert symbol by name. Oh dear. By name. On this table, that's the name length, and that's our operation. Counting the collisions right now probably doesn't make much sense, but let's just count it, why not? All I'm curious is like, does this actually work? So let's make a breakpoint here. Actually, let's also make one here. Okay, we have build errors. Why do we have build errors? GBA insert symbol undefined. That is correct because we have it here. Cool. Index redefinition. So we do, yes. Function GBA symbol table T differs levels of indirection from GBA symbol table double pointer Y, because table is already in pointer and I'm passing the address of a pointer. That is correct. Yep. GBA init table differs from in direction int. What? Right, because we removed the aligning. Okay. Too many parameters. Yeah, I got all this down. Cool. Bam. Okay, table. Capacity is 2, count is 0. Ain't nothing in our little table, which is correct. So we jump in, and what are we trying to add? Well, let's look at the locals. We're trying to add LD. Okay. So LD length is 2, which is completely correct. This is still fine. We do not grow the table. We assign this stuff. We compute our hash, which is 85. Okay. We copy over the name. And indeed, that is the name. And now we go to GBA insert symbol. Okay. So the index we need to insert to is 1. Okay. We check the name length, and name length is indeed 0 because we zeroed all the memory on allocation, which means we can just insert this entry. Bam. And let's see, entry is indeed our LD. Cool, return true. Next insert. That would be LD in lowercase. Our count is 1, capacity is 2, so we still don't need to grow. We compute the hash, which is 149. Oh, I skipped over. No! Should make a breakpoint. Oh, come on, Visual Studio. Let me click. There we go. Should make a breakpoint right here. Okay, so where are we? Right, we're jumping out. Okay, so did this work? That's the question, isn't it? So table, entries. So if I now look at table entries, entries 0, what? Pardon me, it's like this. That should be lowercase ld, and indeed it is. Cool, so it inserted it into the next free slot that it could found, which was indeed number 0, and number 1 is still ld. Cool. Okay, now let's see if growing works. We are trying to insert push. So count equals capacity, and we go into grow symbol table. There we are. We initialize a new symbol table with a capacity of 2. And there we have it, a new table, which is now capacity 4. Sorry, with a new capacity, the double the amount of before. So, right, now we're trying to reinsert all those symbols. Okay, so the first symbol we're trying to add is lowercase ld, which would be on index 1. Okay, and that worked. Now we're trying to insert uppercase LD into also index 1, so we have a collision. So it should put it in slot number 2, so index 2. So let's check. Name equals 0. Nope. Does the name equal? It does not. So we're going to the next index where we will add this symbol. Fantastic. And that was it. We're freeing our old table, setting the table entries to the new entries and the new capacity, and count should still be 2. Yep, fantastic. So we grew our table, and now we can try and insert push. Which should go to index 1, which is full, and index 2 is also full, so it will pop into index 3. So full, full, there we go, we're popping it in. Fantastic. And then whatever the next item is, in this case push in lowercase, needs to go into index 0. We're not growing the table, right, because count is 3 out of 4. Index is 1, because it's quite a small table, so lots and lots of collisions, obviously. One, 2, 3. We reached the end, so we're starting from index 0. Look at the top of the table if there's any free slots available, and indeed there is, so we pop it in there. Turn true. Cool. So by the time we're here on GBA free symbol table, let's just fast forward this, right? Choop. Choop. Our table has a capacity of 128 with 88 elements in there. And indeed the array count is 88. Nice. So that seems to work. So now we kind of need to pre-register all these known names, right? Because those are symbols that are known to us. I mean, there's a few different ways on how you can do it. So for one, at the start of the assembler, we could simply say, right, initialize the symbol table and add all these known symbols right here before you even start parsing the file. The other way, which I personally like a little bit more, is create a symbol table with a fixed size, as a test. Um, so have a simple table with a fixed size. Run our little test program right here where we just um, add all these values into the table, then print out all the symbols in the table that are not empty and print them out with the index, and then just simply hard code them in. Right? So we can do that. Before I do this, so let's. Okay, there are collisions, whatever. Let's print them out, sure. What I want to do now is, can I actually find symbol by name? Let's call it lookup symbol by name, right? The table, we have the name and the length of the name. And what we are getting is GBA symbol T. And if symbol is null, then we print symbol not found. Print F, I mean. And print out the symbol name. Which would be values I. Just to make a check if the lookup is actually working. So okay, let's do it with this size, whatever, doesn't matter. Okay, we have a bunch of symbols not found, which is not good. That is not good at all. It should be able to find all the symbols. Oh boy. Yeah, okay, so what is going wrong? Okay, we have a table with 128 in capacity and 88 items in there, and we're looking up LD. So the hash is this little thing, and now the index is 85. Okay, so we look up index 85. What entry are we getting? Well, we're getting entry LD. So hash oh, I see what happened. No, I don't see what happened. Compute hash hash. So, okay, this must be on the growing then. So if we grow the thing here, no. What on earth? What am I missing? Insert symbol by name. We're computing the hash, which is right here. Okay, we have the hash, whatever. We insert the symbol, which has the index right here. Fine. But the symbol hash is unchanged. Correct. Okay, at some point we grow the table. Yeah, new table. We take the old symbol, and try to insert that one there. Why is this such a small hash for LD? But then when I do this here for LD, it's such a huge hash. $85 is the index. Which, yeah. But how did the index ever end up as the hash? This is so bizarre. Simple hash 85. Name LD hash 85. Okay. And then here, LD. What? I don't know what's going on. I'm such a... It's not 8-bit, is it? It's 32-bit. Ah! Okay, let's fire this up again. And see if we fixed my stupidity. And indeed, we fixed my stupidity. we can find all our symbols. And there's no collisions reported because we constantly grow the hash table. Excellent. Lookup now works. Well, good thing we test this. Let's select an arbitrary size for our hash table, right? 1024. Actually, how big would this be? If we say, actually, no, I don't need to print this out. We can just do it this way. Just set a breakpoint. And okay, we have GBA, actually, size of GBA. Can I zoom in here to make this text bigger? No, of course I can't. Fantastic. GBI symbol table. No, it's symbol table T. So that is 24 bytes. Okay, and then size of GBA symbol T is 272 bytes. Let's fire up the calculator, the good old calculator right here. And we have 272 times this old thing. And then, whoa, oh, what? Okay, and then because I'm super lazy, bytes in gib. Okay. So 272 kilobytes for a hash table. And frankly, that is because because we are using, at the moment there's a lot of wasted space because we allow for 256 bytes for the name. Which in ASCII is 256 characters, which is quite a stupidly long name, right? How about How about 32 bytes? So 272 minus 256 plus, what did I say? 32 bytes times this. And this would be, well, roughly over 4 kilobytes, right? Oh, 48, sorry. 48 kilobytes. And in the worst case, 32 divided by 4. Really? So why divided by 4? Because that is one of the longest UTF-8 runs that you can do. Okay, let's make a little to do because this needs to be reworked somehow at some point. Like this. Okay, to do. Let's say 8. The moment this only allows for 8 times 4-byte wide UTF-8 characters. If Unicode is to be seriously supported, a different counting should be used. I don't know, something like that. So maybe having just a char pointer and allocating these arrays would be the way to go. So if we're doing a string copy, actually allocate memory, you know, and just plug it in there, have like a string buffer or something. I mean, those strings live for the entire run of the program, so I imagine something like that wouldn't be too bad to do. But that's something to consider for later. At the moment, let's just say 32 characters is the maximum. 32 ASCII characters. And then we'll see from there. Okay. Well, I'm quite happy with this. But I do need a coffee and walk a little bit. So I'm gonna just take a break. I'm gonna set this to break and then we'll continue in a moment, okay? See you soon.